In this video, we shall be discussing about the graph coloring using backtracking. So, let G be a graph and M be a positive integer. The problem here is to discover whether the nodes of the given graph G can be colored in such a way that no two adjacent nodes have the same color. Yet only M colors are used. So for example, look into this graph. There is an edge between red vertex and blue vertex. So let me number the vertex 1, 2, 3, 4 and 5, 6, 7, 8, 9, 10. So if you observe, two vertices are said to be adjacent if there exists an edge between them. So therefore, these two vertices wherein this edge is adjacent cannot have same colors to the vertices. Thus vertex 1 has been colored red and vertex 2 is colored as blue. Similarly for this edge 2, when the vertex 2 is colored blue, then the other vertex, that is 3 adjacent to 2, is colored green. Right? So similarly, if you observe throughout in the graph, no two adjacent vertices are having same color. So this is known as graph coloring. So how can this be achieved? So this problem is also called as an M colorability decision problem. Here, coloring of a graph means assignment of colors to all the vertices. The M colorability optimization problem asks for a smallest integer m for which the graph can be colored. And this smallest integer number m, we call it to be the chromatic number of the graph. Some applications of graph coloring are like if you want to schedule an university examination. This problem can be represented using a graph wherein every vertex is a subject and an edge between these vertices mean that there is a common student. So this graph coloring problem, where minimum number of time slots is equal to the chromatic number of the graph. If D is the degree of a given graph, then it can be colored with a maximum of D plus 1 colors. M colorability optimization problem needs us to find out a smallest integer m for which the graph can be colored, and this integer is referred to as the chromatic number of the graph. So you can see this graph, it has a maximum of 5 vertices, so it means that it's sufficient to have 3 colors to perform graph coloring for this particular graph. So let us look into a problem. If you are given a graph which has 4 vertices, 1, 2, 3 and 4, and there exists an edge between 1 to 2, let me call this as edge E1, and the edge between 2 to 3, it is E2, edge between 3 to 4 is E3, and the edge between 4 to 1 is E4. Okay, so we have always seen that backtracking is making use of state space trees to depict the promising nodes as well as the non-promising nodes in order to obtain a solution. So let us start with vertex 1. So how many possibilities do we have to color this graph, right? So let me take M as 3. So now I have three choices. I start with vertex 1. I color vertex 1 with color 1, right? So first time I can color the vertex 1 with color 1. Next time I color it with color 2, that is yellow, and next time I can color it with a color blue, right? So there are three possibilities of coloring vertex 1. So once I have colored vertex 1 as a red, then I have a choice that I must color vertex 2 either by making use of color yellow or by making use of blue color, right? And then once I color second vertex as yellow, then for the next time I can color vertex 3 by making use of red color, or vertex 3 can be colored by making use of blue color. And if I color the vertex 3 with red color, then the last vertex, that is vertex 4, is again left out with two choices. That is, it can either be yellow or it can either be blue, right? So if you observe an edge from vertex, so vertex 1 is colored red, and then vertex 2 is colored yellow, vertex 3 is colored red, and vertex 4 is colored yellow. So if you observe, no two adjacent vertices are assigned a same color. So here in the second possibility, first vertex is colored red, second vertex is colored yellow, third vertex is colored blue, and then the fourth vertex is colored with again colored with yellow, right? We are so if, for example, if I for the second time, if I color the first vertex with red, second vertex with yellow, and third vertex with blue, and the fourth vertex with yellow, it's fine. But I cannot color this fourth vertex again by using red. So therefore you cannot see an edge here going on to vertex 4 with color red, because if I color the fourth vertex with red, then the first vertex is also having a red color and the last vertex is also having a red color. It means that they become adjacent. So similarly, as we already know that backtracking may yield more than one solution to a given problem. So this entire state space tree gives us possible number of solutions to obtain proper graph coloring. So in order to perform graph coloring, we have an algorithm which makes use of an adjacency matrix. So G is an adjacency matrix which has n number of rows and n number of columns, where n stands for number of vertices in the graph and m stands for the number of colors required to perform graph coloring, and we obtain solution in an array called as x, which has n tuples in it. So whereas xi represents the color that is assigned to node I. So now let us look into the algorithm. So we have again two bits to this program. One algorithm known as M coloring and the other algorithm is known as next value. So if you can observe, both the algorithms next value and M color are somehow similar to the Hamiltonian cycle algorithms. So this M color algorithm takes an adjacency graph or adjacency matrix G, which has n number of rows and n number of columns, and tries to assign colors 1, 2, 3 and so on till m to the vertices of the graphs such that no two adjacent vertices are assigned same colors, right? And here k is the index of the next vertex that is to be colored, and this algorithm is making use of recursive backtracking. So let me say, initially we have a solution matrix called as X, which has n number of tuples in it. So if I say that our graph has n number of n which is equal to 4, that is 4 vertices, then this X will have 4 tuples in it, starting from 0, 1, 2, 2 and 3. So now initially all these tuples are set to zeros, and then we start by invoking m coloring of 1. So when we invoke m coloring of 1, then this infinite loop will generate all legal assignments of x of 1, right? So here next value of 1 assigns tries to find out a color and assigns it to the vertex 1, and then it assigns a color and returns a color. So next time this next value moves on to the next vertex and again tries to find out a new color, a legal color, and tries to assign it. And in case it always tries to assign a different color. So we shall look into the code of next value in the next slide. So in case if it cannot return a distinct color, then it returns a value 0. So here when it returns a value 0, you come to the next statement wherein you check if x of k equal to 0. So for example, if I have made a call to m coloring of 2 and I am not able to find a next legal color, the next value shall return a value 0, and in that case if x of 2 is equal to 0 becomes true, then I am backtracking to m color of 1. Are you understanding? So if I have made a color to m coloring of 2 and I did not find a proper legal color for the vertex 2, then it returns a 0. So thus when it returns a 0, I move back to m coloring of 1. So this is how backtracking is taking place. So please remember this particular line, if x of k is equal to 0, then it is used for backtracking. And the other possibility is if all the vertices are colored with distinct colors, That is, if the condition becomes k is equal to n, then what you do is you simply display the contents of the solution matrix. Otherwise, what you do is, for the first time you have made a call to m coloring of 1, so it is assigned a proper color, and 1 is not the last vertex. So in that case you come to else part, and now you make a call to m coloring of 2, that is the second vertex in the graph, and this loop continues until all the vertices are colored. So now let us move on to the algorithm next value. So this algorithm next value of k assigns integer values in the range 1 to m to the adjacency matrix x of 1 to x of k minus 1, such that the adjacent vertices have different integers in them. The value of xk is determined in the range 0 to m, and xk is assigned a next highest numbered color while maintaining distinctness from the adjacency from the adjacent vertices of vertex k. If no color exists to be assigned to a particular vertex, then x of k becomes 0. So for a vertex we start coloring from 1, and if the adjacent nodes have same colors, then we keep on incrementing it till m. So it is achieved by the statement x of k is equal to x of k plus 1 mod m plus 1. That is, you always try to find the next highest color that can be assigned to the vertex k. And while you do this, if xk becomes 0, then it means that all colors have been used and it is not returning you a legal color. Then it simply makes a call to return. So when it makes a call to return, the control jumps back to the function mColor, wherein it again checks if x of k is equal to 0, and if it is true, it is again going to execute a break statement, which means that it is backtracking to its previous vertex, right? And in case if x of k is not equal to 0, that is, you have assigned a new color to x of k, then you again begin with a for loop where j ranges from 1 to n, so that you check to see if there exists an edge between these two vertices k and j, and you have not assigned same colors to vertex k as well as vertex j, right? So if this condition becomes true, that is, if there is a edge between kj and the colors assigned to kj are both same, then again you are going to break, right? Otherwise out, if colors are not assigned, then you are going to come out and you are going to execute the statement if j is equal to n plus 1. That is, if everything is found correctly, that is, if the colors are found correctly, then j is not equal to n plus 1. Then again the control goes back to x of k, which is equal to x of k plus 1 mod m plus 1. And this loop continues until it finds another color. So this is how the graph coloring algorithm works.